We're going to begin a unit today on how fish move. There are many different ways of moving, and the current theme we're going to touch on is yet again how structure is related to function. We've seen a number of different fish in the lab. I think you would all agree they're not all put together the same way. Okay, there's some conspicuous differences in external anatomy that actually have very important consequences for how they swim and how well they're able to swim in different contexts. And one of the things, after covering this material, that you should be able to do is understand and explain how changes in speed occur, how the fish that's attained this, and how that's related to movement and muscle activity in the level of detail that we cover in lecture and on your handout. And we're going to spend a big chunk of time today on actually how the axial structures are used. I think you're already aware that the axial structures can be bent to propel the fish. As it turns out, how that's related to muscle activity is a little bit on the complicated side, but we're going to keep coming back to how the axial structures are used in the locomotion of vertebrates. So it's definitely worth spending a bit of time on how this works in fishes, because if we understand that well, then you can be on top of the issue of, gosh, is it just a matter of, there's a pattern of coordination that evolved in the most recent common ancestor of fishes, and then was retained throughout other vertebrates, regardless of what happened for evolving legs, losing legs, whatever the case may be. Okay? And another thing that you should be able to do is discuss some of the trade-offs in design. This is sort of yet another recurrent theme. Very often, when you're really specialized for doing one thing really well, that may be all fine and good for that one function, but then commonly there's a diminished ability to do something else, okay? Again, sort of that idea is a critter of jack of all trades and a master of none. All right? Let's have you do this individually in the next few minutes. Just make a list, an inventory of the structures that are used to propel fish.
Can we do it on that, please?
Nah, don't worry about it. Let's certainly be prepared to offer up an answer when I call it. It's definitely a good idea to get this written down.
Not much. I was thinking.
Try to think of what you've seen in lab, sort of conjure up a little image of a fish in your head. That's one of the good things about having lab, is that that's some very concrete stuff. So you kind of realize some of the issues. Mhm. Pardon?
I got it on that.
No, no. Is it from the library? Oh, flying pig? Great. So your dad runs?
Name works like that.
Okay, let's see what you came up with. Let's start on the right side of the room, the last row. Someone give me one thing to generate a list of propulsive structures of fishes.
Tail.
Okay. Caudal refers to tail, but I think you mean probably the tail collectively, or the caudal fin, the tail fin, right? Someone in the next row up on this side of the room. One thing.
Pectoral fins.
Sounds good to me. Okay. Next row up.
Is that us?
Yep,
Dorsal fin.
in some cases. Okay. Next row up, just in front of the door. You in there. Yes.
Ventral fins.
What do you mean by ventral?
Like
Is there another
Like
name?
pelvic.
Oh, pelvic fin?
Fin.
So we're going with pelvic fin? Okay. And then between the three of you, someone come up with something.
Are we staying on fins?
I didn't say anything, it's wide open.
Um,
Anything that's used for propulsion.
swim bladder going up and down. 'Cause
That's a little bit of a different issue. Controlling buoyancy is a little different than sort of actively propelling yourself. So, I agree, it's a structure that's relevant and important for movement. But I don't think most folks would think of that as providing a propulsive mechanism. Okay, you have something else?
they're the Myomeres.
Ah, okay. Okay, and how about one of the three of you? Can you add to our list?
Notochordal spine, like any bony structure on the back of the tail.
Okay, so the vertebral column?
Yep.
Okay. And then how about over and around this area? Can you add to our list?
Pec girdle. The girdle themselves.
Okay. How inclusive are you when you're thinking of the pectoral girdle?
I'm thinking skeleton-wise, like if I'm picturing a skeleton, just the movement of where the fins would sit, basically.
Okay, so we do have the pectoral fins on our list already. And they're attached to the pectoral girdle.
Yeah.
But I think it's really more the fins rather than the girdle itself that they're attached to. Any other ideas?
The anal fins.
Ah, okay, good. Anything else?
With any of the adductor or abductor muscles,
Ah,
because I like to look it through, right?
adductor and abductor of what? You don't want the mandibular abductor. We want What can you put in front of a duck?
Pectoral fins, slow it down.
Pectoral fin,
I know,
add it together, yeah. It's kind of like charades, isn't it, right? Sounds like, so there are adductor muscles of the paired fins, right? Okay. Yeah, so you have a combination of structures, muscles that produce force, and then you have a whole bunch of structures that transmit force in some way and move in some way that actually propels the fish, right? So when you're, again, when you're in lab, don't just sort of get so focused on keying everything out. Part of what I'm hoping happens in lab is that you've got this ability to just kind of visualize what a fish looks like, key anatomical structures, and then relate those structures to function. And some of these, in retrospect, are stupidly obvious, but if you just don't take a little second to think about it, it can just, go right out of your mind, okay? Good, so that's a good starting point. And if we sort of paint with broad brush strokes, indeed, what's important to remember is a bunch of the gory details depend on the particular species of fish and the clade to which it belongs, but you mentioned two types of paired fins. Ooh, paired appendages are a synapomorphy for what? More inclusive than performorphs. Performorphs, the synapomorphy, at least the easiest one I find to remember is the fused pectoral and patellar. So those two paired fins are really close to each other. There's a pretty big hint on the slide.
Is it just nappers among
Bingo. Okay. So the jawless fishes do not, and you've seen jawless fishes in lab, they don't have paired fins. Okay. But that's a synapomorphy. Besides being interesting for how fish move, that's a synapomorphy for a huge clade of vertebrates, the jawed vertebrates. And then there are unpaired fins, dorsal fin, anal fin, and at the end of the line, the caudal fin. Another very important structure is the segmented axial skeleton. In nearly all fishes, that's the vertebral column. Again, some of those jawless fishes are sort of a pain to deal with. And then you've got muscles associated with all of these structures that can move and transmit forces generated by the muscles. So adductor muscles for paired fins, if the fins are sticking out to the side, can move the fin towards the middle of the critter. Abductor muscles just have the reverse function. But then you've got all the muscles associated with the vertebral column. So one of the reasons why fish are a good source of protein is that if you look at the total mass of the fish, a very large fraction of the total mass of the fish is muscle. Okay, and a lot of people, if they're carnivores, will get their protein from eating muscle, and the vast majority of the muscle within the fish is in the segmented myomeres. During the course of chordate evolution, what evolved first? Segmentation of the axial muscles or segmentation of the axial skeleton? let's have a vote. Who says segmentation of the axial skeleton evolved first? Raise your hands. You can raise them higher, don't be shy. And then, who says the muscles segmentation evolved first? You remember our little friend Amphioxus and what they look like? Does Amphioxus have segmented axial muscles? Yes. Does Amphioxus have a segmented axial skeleton? Okay. I think it's pretty interesting that, there's a pretty big disparity in time before you get both of those structures completely segmented, okay? So segmented axial muscles have been around for a long time within the chordate lineage. And sort of an intriguing thing to ponder is when you think of how the body of fishes, and for that matter, all vertebrates is put together, a key feature of the body plan is segmentation of those axial structures. And in some cases, there may be hundreds of those when you go from the head to the tip of the tail. So it's very interesting to consider if you have all those little individual units, how the heck do you coordinate their activity to get coordinated movement? Some of us are more coordinated than others. I'm not very coordinated. I'm glad I don't have hundreds of vertebrae because I have enough problems with the few that I can. Okay? So again, if we kind of paint with some very broad brush strokes, you correctly identified the fact that the myomeres are important. And this is a cross section through a species of a relative of tuna. And as shown in some of the illustrations in your book, and as you've seen in lab, the myomeres of fishes are not going straight up and down. They're complicated W-shaped structures. And at the apices of that W shape actually sort of form cones. So envision if you have a traffic cone and then piled on top of another traffic cone, on top of another traffic cone, on top of another traffic cone. If you were to cut through that stack of traffic cones, you'd see concentric circles, right? And so too, that's why for a portion of the fish in cross section, you're seeing that. Besides seeing that, what else is apparent in this photograph of a section?
The vertebral column.
Indeed, the vertebral column is very important.
The nerve cord.
That's important too. But what's another thing we've not discussed yet that you can see here?
The septa that's splitting the.
Indeed, the septa delineate the myomeres, the myoseps. Mm-hmm. Is this photo in black and white or in color? And? What about it?
Blood.
Oh,
It differs, does it not?
Yeah.
Anyone know why it differs?
Is there more blood going to the darker parts and less going to the lighter parts?
That's getting close. That's getting pretty doggone close. There's actually more myoglobin, and that's related to the blood supply. What does myoglobin do?
Carry oxygen.
It gloms onto oxygen that's transported by the hemoglobin. Okay, so it simplified, sort of latches onto it, makes it available for the muscle tissue to use the oxygen. So, how many of you eat turkey at Thanksgiving? And what's a common question when someone's carving up the turkey?
Like,
Yeah, you want dark meat or light meat? Same deal going on here. Okay. The darker red muscle has very important physiological differences. So there are important differences not just in the gross anatomy, but actually in the molecular composition of the muscle tissue. And unlike in mammals, where if you were to take a cross-section of most mammalian muscle, you'd have some red fibers here, some white fibers here, and they'd kind of be all over the place. You get this remarkable spatial segregation in fishes, where in nearly all fishes, the red muscles are just beneath the skin where the lateral line is. And then depending on the species of fish, there will be a different cross-sectional area of that red muscle. And tunas and their relatives actually have a very high aerobic capacity. So that's why I picked this picture, because they've got a lot of red muscle compared to many other species of fishes. Okay? So there are the darkest red muscle shown here is the best at using aerobic pathways to supply energy, but there's kind of a downside in that this muscle does not generate very high levels of force very rapidly. So sometimes you'll see the red muscle fibers referred to as slow aerobic fibers. And then at the other extreme, for those people that prefer white meat compared to dark meat, that's actually fast anaerobic muscle. The anaerobic fibers can generate a lot of force very quickly, but they poop out really fast. They fatigue very rapidly. Often they lose a very sizable fraction of their ability to generate force after maybe about 50 to 100 contractions. And then there's some stuff, depending on the species of fish, that's kind of in between, so-called pink muscle. And there are different names for these, like fast glycolytic, slow oxidative, but don't worry about that. Let's just think of red, pink, white, and then this is the most aerobic, this is the least. So for endurance, it's good to have a lot of red muscle. And indeed, marathon runners have a lot of slow aerobic muscle, whereas sprinters and weightlifters have very explosive movements and don't move very long, and they benefit from having high amounts of white anaerobic muscle fibers. Okay? And then we mentioned that not just along the length of the axial skeleton do you have muscles, but so too at the bases of the paired fins you have muscles that can either move the paired fins toward or away from the middle of the body, adduction and abduction. And cartilaginous fishes and bony fishes have adductors and abductors. But osteichthyes and ray fin fishes in particular have an exquisite ability to move their fins compared to the vast majority of extant cartilaginous fishes. And you've probably seen this in some of the specimens that you handled in lab, where some of the unpaired fins basically are folded down, okay? So rather than being permanently up, an interesting feature of having ray fins is the ability to actually modulate the surface area of the structure. A shark can't do that. And besides having the ability to change the surface area, ray fin fishes have a spectacular ability to actually move the fin rays and consequently move the fin itself. So the entire fin can be moved, but then when you have those fin rays and associated muscles, envision each of my fingers as a different fin ray. You can get some pretty cool patterns of movement within the fin, as well as movements of the entire fin. And the inclinator muscles of the ray fin fishes can move the fin rays from side to side, whereas the erector muscles make the fin stick up and the depressor muscles fold the fin down. Okay? That creates a whole bunch of options for how things are used. So instead of just having an invariant morphology, a really important feature of the ray fin fishes is they can actually vary their shape. That's very important. When shape and surface area are varied, because how things are shaped and how much surface area you have are vitally important for understanding how something interacts with the fluid and is propelled. Okay? There are lots of different ways of swimming. Some of the things that influences how fishes swim are their anatomy, not surprisingly. You've also noticed in lab, I trust, that within a taxonomic group, you generally see rather homogeneous morphology compared to among taxonomic groups. So if you look within a family of fishes, a lot of those species within the family look more similar to each other than if you go outside of that family, or even more distantly related if you go to a different order. Okay? For an individual fish as well as among species of fish, speed is a very important factor for determining what is important for propulsion. Okay? So of course, part of this mix is what are the structures that are used. And another part of this mix that is important is how structures are used. In some cases, you might have the identical structure moved in different ways, and that creates a different mechanical basis for swimming, simply by changing how a given structure is moved. Well, thinking of structures, let's have you spend a couple minutes looking at these pictures of different fish skeletons. Hopefully you would agree they look rather different, but I want you to jot down some ideas in some of the variation among these that has likely important consequences for affecting how the fish swim. Okay? So work on that with the nearest neighbor, and let's not worry about turning it in, but definitely make a list so you're prepared for me to call on.
Yeah.
I guess it's just whatever how big their body is.
Body shape, yeah. And the attachment. So that's right here. Well, a lot of stuff along with number of. Yeah.
The middle one, I guess. You said that.
Like there's like a salt versus like.
Okay, let's see what you came up with. Let's start in the back row on that side of the room. Give me one key thing.
We found the vertebral column length is a lot different. Between just like the one in the top right has a very short spine, while the one in the bottom has a really, really long spine.
Now, what do you mean by long? That this is like a 3 meter long fish and this one is a half meter? Or is that what you mean by long? The absolute length? Or were you kind of getting at a different issue?
It's like if I describe it like basic terms, like the one on the bottom is long and skinny, while the one in the top right it looks short but like added.
Okay, now you're dealing with two things. Length is just one dimension. I like length. Let's stick with length first. How about the percent of the fish that's vertebrate? Okay? Is that what you were kind of getting at?
Like along those lines.
If you look at this length, and then the length from here to here, that's a very high percent of that fish that is vertebrate, right?
Yeah.
Okay? Oops, that one died. So the percent of the total length is the vertebral column. Let's go one row up. Can you come up with another thing?
Is that like how long some of the things are?
Okay, fin length. I'll just use L for length. So you're talking about the distance from where the fin attaches to the body to the tip of the fin. Absolutely, yeah. Next row up.
We said like fin tight, like obviously the wider weight fins give it a more larger surface area, more purchase.
So what do you mean by fin tight?
Well, I guess I'm assuming that's an eel at the bottom. It doesn't really have like the pectoral fins.
Well, eels have them, but it's not in this specimen, to be honest. But then do you mean the, so are you getting at maybe the relative size of the
Yeah,
fins?
the relative surface area.
Okay. Okay. Yeah, it's not just the length that's important. If you think of it pushing against the water, think of trying to paddle a canoe with a 2x4 as opposed to a regular canoe paddle, okay? Bigger surface area in a canoe paddle. Next row up.
For us, we said, the shape of the column thing.
Sure. And next row up.
Number of fins.
Rarely. Okay. Did you just mean like the sum of dorsal?
Well, for example, the bottom one, if pec fin in the front, it only has one set compared to the top left has pec and pelvic fins.
Yeah, I apologize, since this is an anatomical diagram, they're there, but they're not. How about up here? Can you add to our list? Any ideas over here?
So like their shape, how streamlined they are,
Shape of,
of the body of the fish. Like for example, whether or not they're wide or skinny.
Okay.
Head on.
right, so ratio of length to height, or length to width. Embedded within there, you also dealt with a rather different issue, is how streamlined they are. And that's important because, of course, in the fluid, a lot of the work that the animal must do is overcoming drag forces. If you're more streamlined, that's less problematic. Any other ideas come to mind? Anybody? Go wide open.
Would going from like, say your spiny to your softer dorsal legs have to do with anything?
Run that past again?
Like going, like the top left, you go like from spiny to like soft, dorsal raise, whereas.
Okay, so sort of the, then one could refer to the stiffness, right, of the fin supports. Is that what you're getting at?
Yeah.
If you've got a big, fat, rigid spine, that's different than a floppy ray, I think is what you're getting at. That absolutely makes a difference. Rays, I didn't bring my favorite little demo, can actually curl to the side, but spines cannot. Because the rays and ray-fin fishes are actually two paired elements bundled up with connective tissue. And if you slide one relative to the other, it can curl. Number of vertebrae. Okay. Like, this is a puffer, stubby little thing, okay? This is an eel. If you have two fishes of the same length and a bunch of other things are equal, and if you have more joints, you potentially be more flexible. And flexibility and stiffness, whether it's in the fin or the whole body, that's really important stuff. Would you rather paddle a canoe with a paddle made out of a piece of paper or a piece of wood? Wood. Assuming you want to get someplace, right? If you don't care, and if you're just out on the river and you want to work on your tan, maybe you can frantically paddle with paper, but paper would bend, and you'd lose that ability to push against the water, okay? And then, of course, we dealt with depth versus length, sort of a related issue to the percent of the fish that's vertebral column is realize fish heads move in lots of ways, but they don't bend from side to side, okay? So if you actually want to wiggle from side to side to propel yourself, look at what a huge fraction of the total length some of those fish heads are. That's one that's kind of easy to neglect. Where here, the vast majority of the length of the whole critter potentially can contribute to propulsion, okay? There are all kinds of differences in the heights of the neural spines, the heights of the hemal spines, some of the details of how the fins are supported. A whole bunch of stuff varies, and it has important consequences for what is going to work well for propelling the animal. Okay? Well, let's start considering some of the different ways that fish swimming. And again, I caution you on painting with very broad brush strokes here to sort of emphasize commonality rather than some of the oddball exceptions at this point in the game. A lot of the variation you see in swimming fishes depends on how fast the fish is trying to go. And if some of you have had fish as pets in an aquarium at home, you may notice that one that goes slowly may now and then flip a pectoral fin back, and then another pectoral fin, and then maybe another, and then another. But do so in an unsteady way. So we're going to make an important distinction between unsteady movements and steady movements. When I refer to steady movements, a synonym of that would be rhythmic movements, and then I'm referring to events that are spaced evenly through time. Okay, so I'm talking about steady locomotion, that's what I'm talking about, whereas irregularly spaced through time would be unsteady. Okay? And then as the fish needs to go faster, you'll generally see it switching to a rhythmic movement of the pectoral fins. And a bunch of fishes can go reasonable speeds just using the pectoral fins. Notice I'm not mentioning any of those unpaired structures yet. But to go faster still, I think you would agree it makes sense. Use more stuff, get more force, and therefore you can go faster. So at a faster speed, you'll see the retention of pectoral fin movements that are rhythmic, superimposed on rhythmic lateral bending of the vertebral column. And then at some point, and at exactly what point it varies on the particular species, interestingly, the use of the pectoral fins is abandoned. And the fish will go to simply undulating, wiggling from side to side the axial structures. Okay? Why the heck would the fish do that? If you need to go faster, you need more force because you need to overcome increased drag. Why would you abandon the use of a propulsive structure to go faster? Back there.
Would it be so that it can bring its fins in, so it wouldn't be as much resistance?
Right. Remember, the two sides of the equation is the propulsive forces, and then drag is opposing those forces that move the animal. So simply by reducing drag, you can go faster by using the other stuff. Okay? And hopefully it works this time. It's been a little dodgy. Okay. Well, there's a video file on the Canvas site of steady undulatory swimming of a trout. I have no idea why that's not working, but it certainly is working. And basically you can see the pectoral fins folded in. There's a silhouette of the fish, and the fish axial structures are wiggling back and forth in a much more coordinated fashion than I was wiggling back and forth. Okay. And interestingly, at a faster speed still, instead of having tail beats evenly spaced through time, you'll get some very rapid tail beats, a so-called kick and glide or burst and glide mode of swimming. And this is also just referred to as unsteady lateral undulation. And there are a bunch of synonyms for it that I just mentioned. And during the gliding phase or the coasting phase, the fish do almost everything they can to reduce drag. So when they flip the tail against the water, the caudal fin is pretty deep from top to bottom to get a big surface area. But then when they're gliding, you'll commonly see all the fins depressed that can be depressed. So you reduce the total surface area. If you reduce the total surface area, you reduce drag. Okay? And then the all-time gold medal winner for athletic performance is the escape response of fishes. And a whole bunch of stuff happens in about 1/30th of a second. Envision the whole body movement in about 1/30th of a second. And that's the first stage of the escape response, which is not repetitive movements, but basically the fish bends to one side and then bends to the other side. So there's sort of two stages to the escape response that we'll go through in more detail later. Okay? Of all these different types of swimming, there's a huge amount of literature on lateral undulatory swimming. So that's actually pretty well understood. And it's also extremely widespread. So we're going to spend a good little chunk of time going over how that works. This actually is used by jawless fishes, a bunch of chondrichthyan species, and a bunch of bony fishes. Okay. It is not the case that every cartilaginous fish does this, or every bony fish does this. But it is widespread in all of those groups, okay? Again, if you think of some little oddballs like boxfish, which are related to puffer fishes, they can't even bend their bodies, for heaven's sake. So they need to go to a plane feed, okay? So, by way of a quick review, we need to make certain that you remember some things from either your trigonometry class or your physics class about waves. Think of the distinction between a traveling wave and a standing wave, okay? So if the crest of the wave travels along the length of the fish, that is a traveling or propagated wave. And the direction of travel is from head to tail, and that bend pushes against the water. For every action, there's an equal and opposite reaction, right? And so basically then the water pushes back against the body of the fish to provide a component of force in the forward direction. All right? Waves can have many different shapes. Waves may vary in their amplitude. And the amplitude of a wave would simply be that distance to the crest or the trough of a wave. If you have a symmetric wave like this, draw a line through the nodes of the wave, then that's the wave amplitude. Okay? And in the vast majority of fishes that do undulatory swimming, the amplitude increases from head to tail. So unlike this illustration of a simple sinusoidal wave, in a swimming fish, you see substantial variation in how big those bends are. Not only how big those bends are for where the crest is located, but for how long those are. So again, here we have a bend in one direction to the other direction. Those two things together create an entire wave. So then the distance along this axis is the wave length. And that's commonly abbreviated lambda for wave length. L lambda for length. Okay? Now remember that this is a movement. So you have structures going back and forth like this. From the left to the right, events are evenly spaced through time. So you can calculate the time interval from one event to the next time that homologous event occurs. That's the duration of a cycle. And then how many cycles there are per unit time is frequency. So this would be a slow frequency compared to this, okay? And commonly, you'll just see that in inverse units of time for frequency. All right? Well, wave speed, the speed at which a wave travels, is simply the product of frequency times wavelength, which should make good sense because, of course, the units of wavelength are distance, units of frequency are inverse units of time, and speed or velocity is just distance divided by time. Okay? So it's important to remember that the waves are traveling along the length of fish. Okay? What are some key features then of undulatory swimming? One that's actually a little bit on the complicated side is that the speed at which the wave travels exceeds the forward swimming speed of the fish. But it's important to remember that the fish is pushing against the water. And if you think of sort of a transfer of momentum from the fish to the water, realize that momentum depends on mass of something times its velocity. So you can have a big momentum if you have a huge freight train going very slowly because of the big mass. Or you could have a lot of momentum from a speeding bullet with a tiny mass, but it's going really, really fast, okay? And for swimming, a key thing is that thrust, which is another name for the propulsive force, is proportional to this transfer of momentum to the surrounding water. And what's that affected by? Well, that's affected by wave speed and the amount of water that's affected. So some of the logical consequences of that are that if you increase wave speed, you can use that as a mechanism for increasing propulsive force. But another way you can attain a similar end by slightly different means is increasing surface area. Okay. So if you're paddling a canoe, and if you have a great big monstrous paddle, you're going to affect a lot of water when you push against the water. Okay. Now, in a whole bunch of fishes, and again, I'm painting with pretty broad brush strokes here, we see that most commonly they modulate the speed of the waves by modulating the frequency of undulation. There are some subtle changes to the waveform, but the biggest thing to notice is in a swimming fish going slowly, slow frequency, and as it goes faster, you have a higher frequency. Okay? And then, before next time, please look at figures 9.9 and 9.10 in your book. And hopefully, you'll get a good intuitive feel for some of the different types of swimming and how they're characterized by what is actually propelling the fish. And in some cases, in the case of undulatory swimming, the percent of the length of the fish that is actually undulating. So all lateral undulatory swimming is not created equal, as you can see very readily in that figure 9.10 and 9.9 in your book. And also before next time, please stay abreast on these handouts regarding the muscular mechanism of swimming. So you should look in advance at that diagram of patterns of muscle activity and say, what conclusions can I draw from that as we go through that material next time? Okay?